My name is Chris, and I'm the developer of Wargame Simulator, a technology platform that integrates with the physical tabletop. In my day job, I create statistical models that help catch exam cheaters. However, with the recent cheating drama in 40K, I began to think about the problem of weighted dice in wargaming. After following a few conversations, it was apparent that people did seem to think it was likely occurring, but relatively impossible to discover. So I decided to look into it myself. If you don't feel like watching an old wargamer, roll a bunch of dice and talk about statistics. Eject. First, I needed weighted dice, so I purchased 3 dice weighted to roll sixes off Amazon. These are the large black dice with silver pips you will see in every shot. I quickly realized one of my dice was a dud and would only consistently roll a 1 and didn't even contain a 6. So I was down to 2 dice for testing, which I was okay with. Next, I needed a digital system to easily track each roll. I don't trust my own ability to track every roll. Luckily, I had already created a dice recognizer for Wargame Simulator, which could easily and quickly recognize and record every die. This is the system you can see, which is drawing boxes around each die in the video and recognizing which face is up. It is essentially an AI tool, similar to the facial detection on phones, but trained to recognize dice instead of faces. Is it perfect? No, but it is fast and accurate enough. Finally, I needed a methodology. What I came up with is very simple and easy to track on video. Roll dice, including the weighted ones, and record the results. Then, using statistics, compare the observed dice rolls to what was expected. This requires the use of a simple statistical test that tells you whether or not what you observed is statistically different than what was expected. In other words, are the results you see due to chance or something else? When using entirely fair dice, we would expect a roughly even amount of 1s through 6s on the dice rolls. However, we know we are using weighted dice, and we are just seeing if this statistical test will unveil our weighted dice. We have 2 visualizations to help with this. The first is the histogram in the top left. It shows the cumulative dice rolled during each test. We started by just rolling our 2 weighted dice, but then we tried to hide our weighted dice in a set of 4 dice, a set of 10 dice, and a set of 15 dice. Second is the p-value reported below the graph. This number tells us if the current cumulative dice distribution is chance or not. If the number goes below 0.01, it turns red, telling us that there are likely weighted dice in our dice pool. Now, as observers, we know there are weighted dice, and it comes down to whether we will be able to tell they are there and how long it will take us. With 2 dice, it took about 4 dice rolls to determine that the results were not due to chance and that there were likely weighted dice. When we tried to hide the 2 weighted dice among 4 total dice, it took 5 rolls before our p-value reached an unacceptable value, turned red, and was flagged for likely containing weighted dice. As we would expect, when we add dice to dilute the impact of the weighted dice, it does take longer to detect the weighted dice. As we will see, this effect is consistent as we add more fair dice to our pool. Now, we begin rolling 10 dice at a time, 2 of which are still weighted. In this scenario, it actually takes us 7 rolls until our p-value becomes unacceptable. The p-value then bounces around 0.01 for a few more rolls. The big takeaway from this is that when 20% of the dice in a dice pool are weighted to roll a 6, it took us between 70 to 120 total dice to determine that this pool was tainted in some way. Now, if you continue watching, we will begin rolling 15 dice, and notice it will take noticeably longer to detect if there are weighted dice in the pool. We may need 300, 400 die rolls to detect differences between observed and expected dice rolls. Luckily for Warhammer, this isn't a massive problem, as we can expect to reach this number of dice rolled within a single player's turn after you add up all the hit, wound, advanced, saving, and other dice rolls. As the video continues, I would like to discuss my additional thoughts and Warhammer-specific applications. First and foremost, accusations of cheating have to be handled carefully. In my experiment, I used a p-value of 0.01, likely not conservative enough. In a large Warhammer tournament with 100 players, each rolling 400 dice a turn, there would likely be lots of players unjustly accused based on chance, resulting in many Type 1 errors, where we state someone was cheating, but they were not. To reduce this dramatically, we could reduce our p-value to 0.0001, or even lower than 0.01, and stop almost all incorrect accusations. Next, I would imagine that anyone using weighted dice would likely use them at moments that are more important, such as d6 damage rolls, using big weapons, or making crucial saves. So there is likely an inverse relationship between the number of dice rolled and the likelihood of using a weighted dice. This improves detection as we can group all dice rolls of similar size in a separate analysis instead of creating a distribution of all dice rolls. It is hard to remember across a game, but it is very suspicious if all of their damage rolls are 6S, but a dice tracking system will be able to detect that. Finally, there's a very tricky situation of how to deal with someone who has a high likelihood of cheating based on statistics alone. It would be up to tournament organizers to determine how to proceed when someone's dice were flagged for not being balanced. My final thought is a bit of an admission. I did try to run an analysis on the dice used in the Orcs vs. Adeptus Sororitas game that initially caused all this drama, and I would love to report on that. Unfortunately, my dice recognition system could not accurately determine dice rolls used in the event due to them using a die that had a special 6 instead of 6 pips, and the compression of the image on stream also caused inaccuracies. I believe both these issues are easily solvable, enough so that anyone, even casual watchers of a stream, could run the software with only a slight delay to determine the purity of a dice pool. Given that, I think such a system could be used in a live tournament environment. If you have made it this far in the video, thank you so much, and I would love to hear from you.